Okay, hey, welcome back. This is now 12.3. Continuing on with vector valued functions. So we'll introduce here velocity, speed, and acceleration. Acceleration. Long story short, velocity, you'll have a position function, some r of t. And then the derivative of that, r prime of t, is the velocity, which there's my cursive v. If that looks weird, that's for velocity. And then the next derivative is acceleration. So I guess we should put little vector arrows on these guys. So acceleration. And yeah, that's pretty much the long story short. To get speed, you just take the magnitude of the velocity, t, and so the square root of the sum of the components squared. Okay, the geometry of it is basically the derivative gives you the tangent vector. So the tangent vector you can think of as kind of the direction of travel, and yeah, so the velocity vector, you could call it the tangent vector, is what we were calling it before this time. So it's really kind of nothing new. It's just we're putting everything in the context of physics. Computationally, it's pretty simple to deal with. So example 1, they want you to find the velocity, speed, and acceleration vector for this particle described by the position vector. R of t equals 2 sine of t all over 2. I'm going to write it with the angle notation, 2 cosine of t over 2. So we're in the plane here. First, let's get the velocity vector. So velocity is then just the derivative. So we're looking at 2 cosine of t over 2, and then the chain rule, you get a 1/2. So 1/2 times 2 is just 1. So cosine of t over 2. And then the other guy, negative sine of t over 2. Chain rule will get rid of the 2 in the front. Okay, let's get the speed while we're sitting here with the velocity vector right in front of us. So the speed is the square root of the component squared. So we have cosine squared of t over 2 plus negative sine squared of t over 2 is just positive sine squared of t over 2. And then for the Pythagorean theorem, you can see that here, in this case, the velocity is going to be a constant. It's going to be equal to 1. When that happens, your velocity vector and your acceleration vectors will be orthogonal. Let's take a look at the acceleration. So the acceleration vector is going to be given by the derivative of the velocity guy. So what, negative 1/2 sine of t over 2, comma, negative 1/2 cosine of t over 2. Okay. We could go ahead and take a look at this in Calc Plot. So let's see what we got, right? So 2 cosine of t over 2, and then 2, oops, the first one was a sine, sorry. 2 sine of t over 2, and then 2 cosine of t over 2. And let's go ahead and restrict this to 2 dimensions so we can take a look at it. And we can animate it. I have the acceleration and the velocity vector plotted at the same time. So if you go to the little menu, it'll show pretty much anything you want. Later on, we'll deal with the unit tangent vector, the unit normal vector. I don't think we deal with the binormal in this class. But anyways, the velocity vector is the black arrow. The acceleration arrow is the green arrow. Let me put it back to where it began. And you can see the acceleration is always pointing towards the middle. It does not change. I don't think the acceleration really changes all that much in magnitude, right? It's just always the same. That will be from the again, the Pythagorean identities. So if you find the magnitude of the acceleration, it's constant. So it's the same for the velocity. But, okay, so there's that. But they're not always going to be orthogonal. It's only when you have that constant speed. So I think, for example, the next guy is not the same sort of scenario. So let's take a look at the next guy. Example 2, again, we're in the plane still. Sketch the path of the object moving. Okay, so I got to sketch this thing. Squared minus 4, comma, t. Okay, so y is equal to t this time. That means x is equal to y squared minus 4. So it's a sideways facing parabola. 0, it's going to be 1, 2, 3. When x is 0, y. When y is 0, x will be negative 4 down here. And x will equal 0 at plus minus 2. So we have this figure. To get the orientation, you plot a couple t values. So at 0, I'm at negative 4, 0. So negative 4, 0, I'm right here. Then at 1, I'll be at negative 3, 1. So the orientation is going that way. And then at any point, you can, I guess, draw the tangent vector and so the tangent vector, again, is going to be your velocity vector and also the acceleration vector. The problem here, you could get the tangent vector pretty easily, but then the acceleration vector, you want to be a little careful. It's not necessarily going to be orthogonal, okay? So let's get the velocity. So first off, velocity, that will be 2t, comma 1, and then the acceleration vector is going to be 2, comma 0. So it's always pointing in the same direction. In other words, as you move around on this parabola, it's always going to be pointing 2 to the right. So let me put it in blue. It'll look like this, kind of. Okay? No matter where you are. So it's going to be like that here. Going to be like that here. And so it's clear here in this case that the acceleration, hopefully it's clear that the acceleration and the velocity vector are not always perpendicular or orthogonal, right? So I think that was the point of this. And you can take a look at the speed, and you're going to see it's variable, right? So the speed then is the square root of 4t squared plus 1. Yeah, so there's that. Interesting stuff. There's a picture of it. We just sort of did a picture of it. I don't think my velocity arrows were those are also variables, so they shouldn't be all the same size, but hopefully you get the picture. So then they move it up a notch to dealing with the velocity and acceleration vectors in space, but it's the same spiel. So if they give you the position vector here, t, comma t cubed plus 3, and then 3t. Let me put it in our minor, like the angle bracket notation. So there we go. Okay, so pretty simply, to get your velocity, you just take the derivative. So that would be the derivative of the components. So 1, comma 3t squared, comma 3. Get the acceleration. That's just going to be the derivative then of those. So 0, so 6t, and then 0. And what do they want me to do? Sketch a path of the thing? So y is going to be x cubed, I could tell. So at least in the xy plane, it's going to be this thing, and then that's going to extend upwards, and on that you're going to trace the 3t, which is, so this is xy, and then z equals 3t. So at least in the xz plane, you kind of know what's going on there. that would be z equals 3x, so going through the origin and then going straight up, so like that. I don't know. Let's see if I can kind of finagle a sketch of it. Do I dare? X, Y, Z. So we got this plane thing kind of going like this. This would be the trace in the XY plane, and then just kind of repeating itself. So it would be like this surface, and then on that you're going to get you're going to be plotting out the thing, right? So z equals 3x. So in this plane, that kind of z equals 3x. How is it? That's going like this, and then it's cutting through. So I'm not even sure. But never fear. You can always go to Calc Plot if you're super worried about that representation. Let's see what we want to do. So t cubed, and then 3t. And we could plot that. Let's put it into to 3 dimensions, and then yeah. So I guess let's try to animate it. And okay, so let's go back to. So here it is coming in. It's a huge tangent vector there. The velocity vector is just huge with this. And then the green guy is the acceleration vector. It kind of looks like the orthogonal throughout, but I don't know. So yeah. So what else do they want? So they want the. There's the velocity. Yeah, got that. Okay, there's a picture. Well, they want you to evaluate it at t equals 1. So when t equals 1, all you got to do is plug 1 into your velocity vector value function there. So you get 1, 3, 3. And then your acceleration at 1 is going to be 0, 6, 0. Okay, so if they give you acceleration, which, and you know, that's kind of the starting place for developing a position function, you can sort of get to the, yeah, so if they give you acceleration and some initial values, you can get back to the position function. So here they're giving you the sort of beginning position. So this is example 4. R of 0 is 1, 2, 0. They're telling you the acceleration. That's going to be I is 0, J is 1, K is 2. Okay, and they want you to recover. I guess the velocity vector, is that what they want? No, they just want you to find the location after 2 seconds. So yeah, you can start by just integrating the velocity here. So or integrating the acceleration to get to the velocity. So v of t is going to be basically the integral of the acceleration with respect to t. So that would be the integral of 0, 1, 2 dt, and of course that's just going to be c1 comma t plus c2 comma t 2t plus c3. Seems like we need another initial condition, but if you think about it, it's saying that the object is starting from rest. So that gives you the initial velocity. So let me just sort of amend this and put the initial velocity as 0. So starting from rest, that's what that means. Okay, so we should be able to just equate the components of this initial condition here with the velocity vector that I just recovered from the acceleration vector. So C1 is going to be 0, t plus C2. Like I need to plug in 0 for t. Right? So V of 0, that equals 0. So C2 is going to be 0. And then 2 times 0, 0 plus C3 is equal to 0. So C1, C2, C3 are all 0. And so the official velocity vector for this scenario is 0, t, 2t. Then to get the position vector, we can recover that by taking the integral of the velocity vector and then using the other initial condition given in the beginning. Okay, so I need to integrate each of these. The first, the integral of 0 is just c. Integral of t is t squared over 2 plus c2. Then the integral of 2t will just give you the t squared plus c3. The other initial condition is right here. So I borrow that guy, 1, 2, 0. So r of 0 is 1, 2, 0. So plugging that in, C1 is 1. Plugging in 0 for t squared gives you 0 plus C2 equals 2. And then the other one, plugging in 0 for t squared, 0 plus C3 is 0. So officially the position vector is going to be 1 comma t squared over 2 plus 2 comma t squared. Okay, so I think that's what they should get as their answer. Let's see if that's what they got. Yeah. Okay, great. If you want then, so the question asks, find the location after 2 seconds. So all you have to do is plug 2 into the position function. So you get 4 over 2 is 2, plus 2 is 4, and then 4. So 1, 4, 4 for position. Sure, okay. So they're doing a little exploration of velocity there. Let's move on to the next part, which is projectile motion. Which you probably saw this in Calc 2. Now we're actually able to consider the force equation in the plane. So force they're giving you is equal to mass times acceleration with regards to your vertical component. So the J vector. Okay. Rewriting it the way I like to rewrite it. This equals 0 comma negative mg. The downward direction is negative, the upward direction is positive. You could rewrite this then as acceleration because force equals mass times acceleration, right? So mass being a constant, acceleration now being a vector. You have 0 comma negative mg. Then you can divide both sides by m, the mass. So our acceleration is this constant vector negative g. And of course, we're going to use either 32 or 9.8 for our acceleration. 32 for when you're working with seconds or feet, then 9.8 when you're dealing with meters. Okay, we want to sort of recover the position function from this scenario, and that'll cover basically baseball scenarios, like you're throwing a baseball and you know the initial velocity and the angle from which you're throwing it and the height. Okay, so in that case, we're going to need some initial conditions in order to solve it. The initial velocity, which they'll write as v sub 0, they're going to put it into the sort of angle form that we learned. So way back in chapter 11.1-ish, we were talking about vectors. We said we could write it using kind of just numerical components, but we could also write it using the magnitude and the angle. So if you remember, if you know sort of the magnitude of the velocity and the angle at which it is initially thrown, so you'll have v sub 0 cosine of some angle, comma, you could describe the initial velocity in this way. Okay, sine of theta. Then our initial position, we're going to assume, is going to be like the height of the baseball player or where he's throwing the baseball from. So that'll be 0, comma, some number h. Okay. Okay, so we're going to begin with the acceleration and integrate that. So we end up then with the velocity vector equaling c1 comma negative g t plus c2. Then we use the initial velocity to solve for c1 and c2. So we equate components, letting t equal 0. We have c1 equals the magnitude of v sub 0 cosine theta. And then on the second component, when t is 0, negative g times 0 will be 0. So you'll just have c2 equaling the v sub 0 sine of theta. Okay, so we could rewrite our velocity vector as c1, which is v sub 0 cosine theta, and then negative gt plus c2, which is v sub 0 sine theta. Okay, then to recover the position, we just integrate again. So r of t is going to be this junk with a t on it. Okay, so all of this stuff in front of it is considered to be a constant. Then plus a c1, and then integrating the other guy, you get the negative gt squared over 2 plus the magnitude of v sub 0 sine of theta t, and then plus C2, right? So then we use the initial condition, the initial starting position, which would be like the height of the baseball player. So the sort of picture that we're after here is you have a baseball player either throwing a ball or he's hitting a ball. So let's put a bat in his hand. And he's going to hit the ball and it's going to go flying into the outfield somewhere. So there's going to be an angle theta. There's going to be an initial velocity that he hits the ball with, and there's an initial height. Okay. So again, the v sub 0 is the initial velocity. H is going to be our initial position, and of course the initial position is 0, comma h. So I'm saying that r of 0 is again 0, comma h. And then again, you can equate the components and figure out C1 and C2. So equating the first components, letting t equal 0, you get the magnitude v sub 0, well, times 0, that will go away. So C sub 1 will equal 0. And then plugging in 0 into the second component here, the negative g over 2 t squared will be 0. The second part here, the second term, will go to 0. So you just have C2 equaling h. Okay, so ultimately, at the end of the day, long story short, the position function for projectile motion, in particular when you're dealing with baseballs, is going to be the magnitude of the velocity times cosine of theta t, comma, negative gt squared over 2, plus the magnitude of the velocity, initial velocity, times sine of the initial angle, times t, and then plus h. Okay. And that's all derived completely from sort of this picture and the fact that the acceleration due to gravity is this negative g. Okay. Those little arrows are the acceleration due to gravity. They're always going to be pointing downwards there for us. Okay, so in an example 5, they just did what I just did. Long story short for that. Example 6 is an application. I say let's just go to the homework and start kind of doing some of those. Okay, so this is 12.3-ish. And let's take a look at some of these. These are computationally, they're kind of annoying, to say the least. So I like this number 8. I posted it on Facebook. I think my mom enjoyed it. She's a big Indians fan, baseball fan, so she would kind of understand it. but if, you know, she probably didn't understand calculus or anything, but I think she got the idea. So what's happening here is you have a baseball player at second base. So hopefully you guys have played baseball, or at least have watched baseball. Here's the pitcher's mound. This person is throwing the baseball to the first baseman. Okay, it's not going in a straight path, it's going in a sort of a parabolic path. I don't know where it's hitting the first baseman is the issue. Right, so the baseball player throws the baseball 90 feet. So this distance is 90. Be careful about the units. Sometimes they'll try to mess with you. Oh, in this problem they do. So look, they put 50 miles per hour. You've got to convert that to feet per second. So that's one minor annoyance. The baseball is released 5 feet above the ground. So this distance is 5. The initial, that's the h distance. H equals 5. Initial speed is 50 miles per hour with an angle of 13 degrees. So that basically tells you the magnitude of the velocity at time 0 is 50, but we're going to have to convert that here in a second. So, you know, whatever, 3,600 seconds in 1 hour, and then like 5,000 feet in a mile. Feet, miles to feet. Miles to feet. Why is it not miles? Work out. Miles to feet. 5280. Jeez. Okay, so 5280. That looks like a real headache there for us. Insult to injury type situation they like. All right, so there's that. Then they tell you theta is equal to 13 degrees. The ball is released 5 feet above the ground, initial speed of 50 miles per hour, angle 30. At what height does the baseball player catch the baseball? So this point here that the baseball player, the other guy is catching it, it's supposed to be a mitt or something. That point is going to be 90 comma something. Okay, I don't know the height. That's what I'm trying to find out. But the x coordinate, the distance x is 90 feet. I just have to figure out the height, y. All right, so I could kind of set up my projectile motion function, vector valued function here, just from this knowledge. So I'm plugging in the magnitude of v sub 0. Oh, let me figure what that is. I got one calculator that'll do fractions for me, so I'll get that out. What do we have? 50 times 3,600. Jeez. Really? I'm just going to do a Wolfram and Wolframize it. Wolfram alpha. There's so many, it's so easy to make mistakes in here. Please don't send me emails asking me to check your work for errors. I don't have time to go through everybody's, you should be finding your own errors at this point, hopefully. I mean, if you have to be really, really careful with your work. You see, I'm not being very careful. You have to be very organized. 371. It's strategically positioned so I can't read as I write. Okay, there's that 375 over 11 seconds. Do I got it upside down? I do, don't I? So 50 miles per hour. I want, there's, in 1 hour there are 3,600 seconds, and then in 1 mile, sorry guys, there are, what would I say, 5280. If I'm not right, that would screw up all my computations. So you gotta be super careful. 5280 is correct. Let's go ahead and rewrite that. So 50 times 5280 divided by 3600 is 220 over 3. Okay. Jeez, that's a mess. I have 220 all over 3 times cosine of the angle is 13, and it's all of this is times t, comma, basically the same thing, but with a, and then g, because we're in feet per second, g is going to be the 32 this time. So negative g t squared over 2 is going to end up being negative 16t squared. So negative 16t squared. And then plus, let's go ahead and put the 220 all over 3 sine of 13t. And then plus the height, and we said the initial height was 5. Okay. Okay, so I think now, okay, so what I'm looking for is basically this y coordinate of this ordered pair. So if you let the x component equal 90, in other words, you go 220 all over 3 cosine of 13, t equal 90, you could solve for the t, the time at which that happens, and then just plop that into the y formula, the y component formula. So let's see what we get, right? So I have t equals, and this is where I make all kinds of mistakes. I just try to do too much in my head. But anyways, 3 times 90 is 270. 270 over 22 is 27 all over 22. And that, I probably made a mistake, right? I sure hope not. All over cosine of 13. And then there's all right, so the 90 is good, 270, okay. Then I'm going to plop this value, this t value, into this formula. And that should tell me the y coordinates. So y would equal, this is, first one's from x, but y equals negative 16. And then I got to plop this guy in, which is a nightmare. Squared plus this next guy times t. I'm trying to give myself a little more room. It's not nice about it. 220 all over 3 sine of 13 times the 27. See what a mess this is. 22 cosine of 13. And then plus the 5. Okay, I'm going to try to just put it into Wolfram over here and hope for the best. So negative 16 parentheses 27 divided by parenthesis 22 cosine, and of course it's going to be a jerk about the fact that it doesn't know if you're in radians or degrees. Let's square all of that. So this thing is squared plus 220 over 3 star sine of 13 times 27 divided by 22 cosine again of 13, and then all of that in parentheses. Right, plus 5. It should give you a nice kind of looking. Okay, so good. It gave it to me in degrees. 0.394. Okay. So the height is ultimately 0.39. I don't know how many decimals they want. 3 probably. Right. Yeah, 3 decimals. 394. Yeah. So on Facebook, my mom, she enjoyed the problem. One of my other relatives, she said it was the guy on a trampoline, the guy that on first base that received the throw. That didn't make a lot of sense. What really seems to be happening is the guy is throwing it from second base to the first baseman, and basically the dude throws it and it goes right at his feet, and he caught it right at his feet. So I was like, I put it on Facebook. I said, hey, nice snag, right? All right, so anyways, there's that. Let's look at another one. Let's try number 7. We'll make that the video quiz as well. So let me mark down that this is the video quiz, and then I'll sort of lead you to your own devices. But yeah, again, I cannot emphasize enough. You have to be very careful. Hopefully you are very awake. You just drink all your coffee. Well, maybe coffee will make you nervous and make you make mistakes, but anyway, 7, this is our video quiz. Getting better about noting the video quizzes. Right, so this is the 3rd video quiz, and video quiz set number 3, and it is problem number 7 from WebAssign. Okay, so let's take a look here at what's going on. Use the model for projectile motion again. Baseball is hit, it's 3 feet above the ground, so H is automatically 3. Leaves the bat at an angle of 45 degrees. This one may be too easy for us. I bet that last one is kind of be annoying. Oh, in the last one, when you type in your answer, you can't just type in theta. You have to type in theta sub-0. I could not figure out what was wrong, you know. So you have to use like this button and click that, and then the Greek theta, and then sub-0. Otherwise, it'll mark it wrong, and you'll be like, "What is going on?" It's a monster of a problem. Maybe we should do that one instead, just so you have it in your notes. Let's do that. Sorry. So video quiz is actually number 9. Okay. So sorry about that. And I think this will be helpful because I would probably want you to use the computer on this one, and I'll show you where. Okay, so sorry, video quiz is number 9. Mark that in my notes. Okie dokie. So this one's brutal, as I remember. I made all kinds of little mistakes in it when I did it. Anyways, a certain baseball field in Ontario has a center field fence that's 10 feet high and 420 feet away from home plate. So here is home plate. This distance is 420 feet, and then there's a fence out here, and the fence is 10 feet high. Okay. Let's see what's happening. So the ball is hit 3 feet above the ground, so H is equal to 3. It leaves the bat with a speed, so V sub 0 is 100, but we got to convert that. So 100 miles per hour. So in 1 hour, there are 3,600 seconds. And in 1 mile, there are 5280 feet. Okay, so let's clean that up really quick. So 100 divided by 3,600 times 5282 is 440 all over 3. Okay, so this is 440 all over 3. Let's see what they want. I want you to move over. So I'm not cramping my style, all right? Okay, there's that. So certain baseball field in Ontario has a center fence that's 10 feet high and 420 feet away from home plate. A ball is hit 3 feet above the ground, leaves the bat at a speed of 100 miles per hour, which is 440 thirds feet per second. The ball leaves the bat at an angle of theta equals, so you don't know theta sub 0. That's the hard part about this problem. So theta sub 0 is kind of unknown, but we could build our equation, and that's kind of what you see there. That's what they want for the first answer. So R of t is going to be 440 thirds cosine of, and they want you to put theta, again, they need theta sub 0. And then comma, there's a t on there, don't forget the t, comma, 440 thirds sine of theta sub 0 t. And then, minus the 1/2 gt squared, so 32 over 2, negative 16 t squared, and then the initial height is plus 3. You don't necessarily have to put the terms in the same order as I did. Okay, so there's that. Use a graphing utility. I'm not going to use a graphing utility. I'm just going to get the answer and find which one's appropriate. Okay, so the way you kind of pull it is they gave you this initial condition here, which is basically an ordered pair. They're saying when x is equal to 420, the y is equal to 10. Okay, so you use that factoid in order to eliminate one of the variables and then do a substitution. Okay, so you're going to set the x component equal to that. Or 20. Okay. I'm going to solve for t. So t equals, and now this is where I usually screw things up. So let me go to Wolfram. It's going to be 420 times 3 divided by 440. So t equals 63 all over 22 cosine of theta sub 0. Then I'm going to take that expression and plug it into the y expression and set it equal to 10, the y coordinate at that point. Okay, so I'll have 440 over 3 sine of theta sub 0 times t, which in this case is 63 all over 22 cosine of theta sub 0, minus 16 times t, which is 63 all over 22 cosine of theta sub 0 squared, and then plus 3, and then I have to set that equal to 10. I'm going to move everything well, first I'm going to, believe it or not, I'm going to rewrite everything in terms of tan. So how do I do that? First, let me clean it up a little bit. Again, on this first term, I have 440 over 3 times 63 over 22. There we go. Sweet. So the coefficient here is 420. I've done it before, so I knew it came to be an integer, which is why I'm so happy. Okay, and then it's sine theta sub 0 over cosine theta sub 0. That's really tan theta sub 0. Okay. And then minus this other nasty component is 16 times 63 squared divided by 22 squared, okay, which is a nasty one. 15876, I think it was over 121. I hate it when it does this to me. 15876 all over 121, yeah. And then 1 over cosine squared is the same as secant squared, theta sub 0, plus 3 equals 10. I think then we can kind of, no, I need the calculator still. Right, so I'm going to get rid of the 121 first off. You might as well move the 3 over, but I'm going to multiply everything by 121. Okay, so 420 times 121 is 50820 tan of theta sub 0 minus 15876. Then I'm going to convert secant squared into 1 minus tan squared of theta sub 0. and that will equal 7. Then I'm going to, well, I guess I could leave the 7 on the other, I should put the 7 on the other side. But anyways, 50820 tan of theta sub 0 minus 15876 plus 15876 tan squared theta sub 0 equals 7. Move the 7 over, rewrite things so it's kind of in a quadratic form. And I don't trust myself to even add 7 to this thing. I've screwed up these problems so many times, it's just... Okay, so I'll have 15876 tan squared theta sub 0 plus 50820 tan theta sub 0 minus 15883 equals 0. And then this is where I want you to use the computer. So tan of theta sub 0 will equal. So you could just go over the Wolfram and solve it as a quadratic. So solve basically 15876 squared plus 50, what the heck number is that? 820x minus 1588 with respect to x, and that has to equal 0. So you put solve, then parentheses, put the equation, and then the variable you want to solve for. And it should give you an output. Let's get approximate. It gave me 2 answers, and both of them look like they're wrong. 15876, 50820, and 15883. So it's very easy to screw these up. So there's 2 answers, and that just means there's kind of like 2 parabolas that will get the job done. There's one that goes up, and then there's another one that's going to go like this. I think they want the, okay, so anyways, tan of theta sub 0 will equal negative 3.488, or tan of theta sub 0 will equal 0.28683. You just do tan inverses on those. So arc tan of negative 3.488. Let's just use the number there, 4879. So that's definitely not what we want. But I think we're in degrees, so that might have been in radians. So definitely not right. So let's try the other one. 0.28683, and that's not right either. Maybe that was in radians. It's degrees, 16 degrees, so that's wrong. So I made a mistake somewhere, so I'm going to pause the video and figure that out. Okay, and I'll be right back. Okay, it's, believe it or not, is the same mistake I made when I practiced it. It's wow, you just make the same idiot mistakes over and over. Does anybody know what it is? It's I forgot to multiply by everything by 121. So this should be 7 times 121 here. So that would be this right here. 7 times 121, 847. And then when I subtract that over, this guy will be different. 15876 plus 847 is 16723-ish. And there's one other thing too. Oh, this identity right here, it should be 1 plus tan squared. So then this cat right here will be negative. When I pull this over, it's going to be negative. And what? So this one is negative. And then when I move the 847 over, that's going to give me negative 16723. And then I'm going to move everything, or multiply both sides by -1. I got 1587610 squared, theta sub 0, plus 508210 of theta sub 0. Whoops, minus. See, there's just so many things going on. And then plus 16723 equals 0. That's the thing I'm going to solve. It would be great if I hit the accidentally hit the X button there. Adding insult to injury. You got to make it so I can see it. Okay, so whatever. 15. I almost had it. So this should be a minus. And then plus 16.7 plus 16.7 2 3. And then push enter. And okay, it's approximate. So tan of theta sub 0 should equal 0.3723. 0.37238, or tan theta sub 0 will be 2.8287. And then I'm going to take tan inverse of those guys and figure out which one is good. Tan of 0.37238. And I want degrees, so that's 20 degrees, 20.42 degrees. This other guy, it's probably not going to work for me. 2.8287. So big 70 degrees. 3 degrees. Okay, so going back to the question, then you see the 70 degree option isn't even there. The closest one is the 20 degrees, so you hit 20 degrees. And then determine analytically to 1 decimal, 20.4 degrees is the angle. Okay, so yeah, you have to be really, really careful about writing out your work and kind of making sure you copy things down correctly. And then there's these huge numbers and all kinds of angles, and it's just a literal nightmare. It's almost like if you are good at accounting and stuff like that, you'll probably be good. But if you have sloppy work, you're going to have to tighten it up. Okay, you're going to have to tighten that up. Start using, what I started doing is using bigger sheets of paper. If you're like got a brother with a sketch pad or something, one of those bigger sheets, do that. You got to figure out a way to make it look real organized. That way you could spot the mistakes and you're not spinning your wheels for an hour, or worst case scenario, emailing me and trying to get me to do your work for you. Okay, so you got to figure out a way to catch your errors and mistakes. You can't be doing that at a job, Imagine you're at a job and you're doing your work and you think, oh, I think I made a mistake. I'll just go to my boss. No, you got to figure out your mistakes, okay? You got to figure them out and figure out a way to do them. So I think organization is number one. Always check for the silly errors. Check to make sure you copy the problem down right. Check to make sure that all your additions are correct. The steps that you do in your head, they're real easy to make mistakes. So I try to do as little as possible in my head because I make so many mistakes, especially if I'm tired. Okay, so you know what you're up against, right? I hope you know. You do not want to make mistakes in the real world. Mistakes cost you millions of dollars. Okay. I mean, here you're safe, you're okay. You could still send me an email and say, hey, what's wrong? I've been working for 4 hours on it. I can't find it. But yeah, you got to figure out a way, Okay, enough of that. Okay, thank you for watching as usual, and I'll see you next time.